Hello, everyone. I am Arsalan, and I'll be presenting a short overview of our work on Gibbs sampling on quantum computers. This is a joint work with Pooya Rongh. Um, okay, let's get started. What is the Gibbs sampling problem? In the Gibbs sampling problem, we're given an oracle excess to an energy function E, and we would like to draw samples according to this distribution written here. One of the main reasons this problem is hard is because of this partition function that we don't have access to a priori, right? Given just an oracle access, we cannot easily compute it. And I should say that this problem is a really hard problem. We do not expect classical or quantum computers to be able to solve it efficiently. What are the applications? Well, you can see that you can choose beta large enough to sample from the points X where E attains its minimum. You can use it in training energy-based models. The reason being, when you're doing trainings, you're taking derivatives, and taking derivatives in thermodynamical formulations becomes like computing expectation values, and computing expectation values can be done by drawing samples. So, and as the last application that I'll mention here, we have counting. You can compute counting in the continuous domain would be like computing volumes, right? So you can compute volumes of objects if you can draw samples according to specific distributions. One instance is like when you have when you want to, like in elementary programming, we can compute the area of a circle by drawing samples from inside of a box and then seeing how many of those are inside the circle, right? Next, I'm going to show you the results that we get in using our algorithm. There are two columns here that are important to us, sampling and mean estimation. You can see that we can achieve, like, this work achieves advantage over classical algorithms for sampling. Moreover, we don't have a dependency on epsilon. Sorry, for mean estimation, we don't have a dependency on epsilon for mean estimation, meaning that there is a hidden polylogarithmic dependence, and by this O tilde. And you can see that in certain cases, for instance, where your function has some geometrical condition called Morse, we get some quadratic advantages. Overall, our algorithm outperforms the state-of-the-art at high temperature and high accuracy. I think that if there is one lesson to be learned from this work is the following: that quantum algorithms can solve Fokker-Planck equation. So what is the Fokker-Planck equation? There is this Langevin dynamics written here that it allow you to generate samples from a given energy function. Note that you don't really need to have the information about the partition function to run this stochastic differential equation. And it's like a Monte Carlo, like there are Monte Carlo basically methods developed out of this fact that this SDE achieves a Gibbs distribution at time infinity. However, there's like an equivalent formulation of this problem, which is to look at the evolution of the probability distribution of a particle under this SDE, and that would become the Fokker-Planck equation. Classical computers cannot simulate Fokker-Planck equation efficiently because there are exponentially many points at high dimension that describe this function P. However, due to recent breakthroughs in quantum algorithms, basically, we know that there are algorithms that solve differential equations over exponentially many points efficiently. One example of such is this paper cited in our work. And now I'm going to, like, the second bullet point here, that the normalization constant Z that's provided to us by the universe, like of quantum, by the quantum universe. Every state should be normalized, right? So if you prepare something, you know that it should be normalized. However, the cost at which you can prepare the state is the post-selection cost. And our analysis in the paper shows that this post-selection cost is related to the mixing time. So that's the the hardness of solving the problem going through this focal plank method. As a result, I think I just want to say that you cannot get a fast forwarding in time, and however, you can get you can basically use differential solvers for sampling, which is a novel thing we present. Now, a main tool that we developed in order to solve our problem is the interpolation method, which says that if you have an endpoint discretization, you can transform that into an exponentially many point discretization, only with a polynomial complexity. Here we're assuming that the function, the underlying function that we're interpolating is analytic. And we show this nice correspondence between analytic functions and sub-exponential distributions. Basically, if f is an analytic function, then its Fourier transform f hat has this property that this guy is a sub-exponential distribution. The normalized Fourier transform squared is a sub-exponential distribution. And then, there are like quantum Fourier transform techniques that we'll use in order to devise an algorithm which basically proves the theorem above. Okay. Having said that, I should also mention that I believe this interpolation technique could be applied broader to a more other problems as well. And it could have further application. Thank you very much for listening to me.